notes, but we're just going to pass this very fast, okay? So we were discussing this aspect of possible solutions of the differential equations. We move to a general aspect, which as a reference regarding these, it looks like there are some publications from the 80s where they have analyzed the polygonal loop antennas. Now, often, in order to get a closest solution to the distribution of the wave from an antenna as a function of theta and the phi, often these are done by using numerical techniques, or you need to write a program for that to scan the whole three-dimensional space in spherical, cylindrical, or Cartesian coordinate system. In some studies, researchers have figured out for possible configurations regarding the loop antennas, where square, triangular, rectangular, and rhombic are some of those. So these polygonal loops, they might look like the square. We can have an antenna which is has a triangular shape. Triangular shape. It is so we have it can be also what is this top-driven triangular, which is driven. The generator is from the, so you can see the generator. We denote it like an AC type, top-driven triangular antenna, base-driven triangular loop antenna. So the generator is at the bottom of the antenna. And then here we have a rectangular antenna. We have also a rhombic antenna, so all of these possibilities, but this says the most attractive ones are with the largest bandwidth. Apparently, they are the triangular, rectangular, and rhombic. Ferrite loop antennas. These antennas actually, once you talk about ferrite, it means that it has some iron component in it. Okay, so it's like ferrum, like you know that what is iron dioxide, iron trioxide, which relates to the how ferrum is linked with molecules when it is oxidized. We see that, and there are components which are really good to some degree for antennas, because they have specific value for the permeability. Let's have a look at relative permeabilities of ferrite materials, which are iron-like materials. For example, iron, it has a relative permeability of 5,000. Purified iron, which is pure ferrite, it is 200,000 magnetic, sorry, let's call it just permeability. Typical is in the order of 1,000. So 10 to the power 3 to 10 to the power 5, it's a huge range for the permeability. And now, assuming that we have these different permeabilities, which are large, we can obtain the ohmic resistance for all of these components. But now that all of these values, they are strongly magnified or modified by the huge value of the respective permeability. So the equations that we have seen so far, they are similar to what we had before, modified slightly. Okay, so we have one turn, n turn. Use of loop antennas. Okay. These are where the loop antennas are used. Loop antennas are more immune to noise and makes them more attractive for an interference fading environment, like a mobile communication system. Loops can be mounted either vertically or horizontally. Mobile systems. Okay. Okay, so with all of these, oh, I thought we are over. So let's see, loop antennas on a box. For frequency below the first resonance, the impedance is inductive. Impedance is inductive, yes. Okay, about the first, okay, so below the first resonance, let's see here. So we have the first resonance handheld mobile device system. So from this graph, we see actually let's say the reactance, and we notice that there is a resonance for the reactance in the ohms in the order, something in the order of 900 megahertz. Now this 900 megahertz, which could start as low as 750 to 900 megahertz, this is in fact the old communication frequency which has been used for cell phones in United States and Europe. I always mix those. I think Europe used to use 800 megahertz and US was 900, so that was the first, it was like this. The second generation of cell phones, they immediately jumped for both continents to 1800, so it was twice the American frequency. So it was easier than to sell cell phones, to buy in US and use them in Europe and vice versa. So this was solved. But this was, now I'm relating this one to the resonant frequency, which happens for the loop antennas. Now, this around 900 megahertz, this is the first resonance. If the frequency used for communication is below the first resonance, apparently the impedance is inductive. But above the first resonance, the impedance is capacitive. Because, so on the first case, it might lead the one variable with respect to the other, but after that specific frequency, it will lag behind. Pra nëse përpara frekuencës caktuar, një masi është përpara në fazë se tjetra, në krau më tan do ngelet mbrapa. So we have a second resonance, the pas një resonance e dytë 21 herë 100 ose 2100 MHz. 2100 MHz kemi diku se e lexon këtu kjo, apo pse se lexon këtu kjo thot 2100. Në grafiku nuk duket qartë. Okej, pra deri tani thjesht pak a shumë elementet you're presenting, stop presenting, disa elementë të rëndësishëm në lidhje me antenat në përgjithësi. Tani elementi i radhës që mund ta duhet neve për të pasur pak parasysh. E para, gjithmonë duhet kemi intuitën e përgjithshme për sa përket antenave. Dhe analiza fillestare intuitive ka të bëjë shpesh qoftë edhe me njësinë e masive me cilat po punojmë. Pjesa e dytë pasi që na duhet neve për kapitullin e antenave është të shikojmë me kujdes këto ekuacionet, nuk e dia e kam fokusuar mirë këtë materialin, por do shikoni nga libri faqen 274, pasi keni gjithë ekuacionet të cilat do t'ju ndihmojnë për zgjidhjen e shumë problemeve nga libri. Tani në lidhje me këtë, kënd diçka me këtu. Në lidhje me këtë, patjetër që analiza e intensiteteve të lup antenas, sidomos në rastin kur ato janë vogla, kur janë thjesht të përgjithësuara, ajo është pak e vështirë, po mos u stresoni shumë për atë pjesën. Pasi we don't always cover that. Ju se nuk e we don't cover. Por kur futen këto ekuacionet e funksionet e polinomeve të Bezelit, atëherë mund përdorim shpesh integralet nga tabelat. Le të shikojmë një shembull këtu. Për shembull, le të konsiderojmë për një moment. Konsiderojmë sikur kemi një antenë të vogël. Kur themi antenë në kapitullin e 5 e fillon direkt me antena që ishin relativisht të vogla. Pa thonim small antenna, pa përdorur fare approximations dhe do të pyetëm atje kjo, për shembull, i gjet dëm. So we have a small antenna. mund të gjejmë directivitin. Normalisht, ajo që duhet shikojmë, normalisht zgjidhen kësaj pothuajse kemi dhënë gjatë slideve. Po thjesht ky si shembull mund të shërbejë si reminder. Këto small antena ne pamë gjatë slideve që fusha elektrike ishte diku proporcional me sinusin. Dakor, ishte me sinus teta. Dhe nëse kjo është fusha elektrike, është proporcional me sinus teta, atëherë radiated power është proporcional me sinus në katror teta. Nëse është proporcional me sinus në katror teta, për të gjetur directivity dhe parametrat e tjerë, çfarë na duhet neve? Duhet të integrojmë këtë radiated power density përmbi një sipërfaqe me rreth me distancë r, po integralin e marrim për të bëjmë integralin e saj, do të integrojmë sinus teta d teta d phi. Pra, në sens, do të jemi të bëjmë me sinus katror, që shumëzon edhe një sinus tjetër, që bëhet me sinus në kub. Sinus teta, po. Pra kemi këtë shprehje. Për shembull, kur të jemi provim, unë dëshiroj për jush, ose nga të gjithë, fakt, që këtë integralin, nëse do e zgjidhin, ta bëjnë hap pas hapi. Edhe nëse nuk e zgjidhin dot, që mund të jetë pak e vështirë, ta tregojnë të paktën hapa që ndiqen. Pasi po të tregojnë hapa që ndiqen, thjesht mund të bëjnë një notë të kështu, që ka humbur disa pikë. Për shembull, në këtë rast, nuk përdoroj gjithmonë intuit në këtë situatë, për shembull, këtu sinus katrorin, e para d phi-ja njëhet mund ta lëmë në një, sinus katrori është 1 minus kosinus në katror teta, këtu kemi sinus teta d teta, mund përdorim zëvendësim variablesh, unë mund ta quajmë kosinus teta, unë është barabartë me kosinus teta, d-uja është barabartë me minus sinus teta d theta. Për shembull, këto lloj zëvendësimesh në integrale që mund të keni detyrë shtëpi ose provim, duhet i tregoni, nëse i tregoni dhe prapë integrali ka dalë gabim për punë numrash, nuk ka problem fare. Por duhet të shikojmë që ju të lodheni pak me këto. Sa mund të të lodheni pak ku gjejmë këto lloje integralesh. Ose në këtë moment ne shikojmë që këtu kemi 1 minus punë katror, që është kjo du, pasi kjo do të jetë uja, pastaj kemi integralin e du minus u katror du. Pra është 2pi du minus u katror du e kështu me radhë. Pra po të vazhdojmë me këto lloj integralesh, ne mund të gjejmë që radiated power, këto shikojmë, nuk përdorem këtu. Për radiated, dhe diçka tek 8pi të treta, në fakt 8pi të treta, këto dhe rezultate që kemi parë shpesh në rezultatet e drejtanishme. Edhe këtë kemi 8pi të tretat, ajo që na intereson tjetra është vlera u maksimale. Shpreha d sa është d-ja, është u maksimale pjesim për p radiated, po s'marrim 4pi. Atëherë këtu kemi 4pi. U maksimale pjesim për p radiated. Atëherë këtu pak a shumë kemi që kjo u maksimale një sekond. Thjesht për pasi shka parasysh, që eja tradicionalisht është proporcional me sinus tetën, por gjithashtu 1/r. Nëse kjo është 1/r, kjo radiated power është 1/r në katror, dakor? Pra, eja që mund shkruhet si disa konstante, që shumëzon sinus theta 1/r. Radiated power është disa konstante që shumëzon sinus në katror 1/m², dhe radiation intensity, që është uja është barabartë me r katror, që shumëzon radiation, kjo është radiation intensity, kjo është power density, radiation, kjo do të jetë barabartë me r katror, që shumëzon sinusin katror 1/r², për këtu në angjilet do të thënë sinusin katror theta. Pra në këtë situatë, takon që u maksim mund të jetë barabartë me 1, pasi vlera maksimale e sinusit është 1, dhe directivity d-ja që kemi të shprehur këtu do të jetë barabartë me 4pi, që shumëzon u maksim, që është 1, nissim për 8pi të treta, këtu ikën, me kjo del 3 të dytat. Pra ne gjeni directivity të barabartë me 3 të dytat, kjo është në si raport me decibel, por llogarisim 10 që shumëzon logaritmën e 1.5-ës, gjem 1.76, ose mirë është të shkojmë gjithmonë të dy vlerat e d-s, si me decibel, por edhe tjetër. Çfarë kemi të ne? Okay. Zëmë se kemi një circular loop që do e përdorim si antenë, dhe kemi n-ja është barabartë me n. Thjesht për thonë që kemi disa loope, dhe këtu kemi current distribution, është uniform, I-ja është barabartë me I0, që shumëzon A phi. Kjo do thotë që është current distribution është uniforme, pra nuk I përket rasteve komplekse. Tjetër element rëndësishëm kemi që kjo ka një circumference që është lambda të treta, pra C për marrë lambda pjesë për 3, pra është një treta e gjithësisë së valës me cilën po punojmë, dhe kemi lossless transmission line, dhe kemi një transmission line, kjo është të lëja, e cila po e quajmë të formë, thjesht po mundohemi të interpretojmë se si lidhet transmission line me loop antena, dhe kjo transmission line ka një impedancë që është barabartë me 250 ohm. Okay? Kjo është impedanca që ka të lëja. Kjo është impedanca që ka të lëja. Çështja është të gjejmë në such that, let's find n such that the impedance of the antenna, let's call it like this. It is approximately to the impedance of the transmission line. Okay. So let's try to find out what is an approximate number that will allow us to have a matching of the impedance right here. Okay. Because we don't want, so once the signal is coming through the transmission line to the antenna, we don't want a huge back reflection of the signal. So let's find this one, and okay. But regarding this, I have to look at the equations from the book. So I can strongly suggest to you, have a look at page 274. You can have a look at page 274 for the relevant equations, which are hard to memorize. So okay, so we have these values, and now wait a second. So initially we have to find out what is the value for the resistance. The radiation resistance, it can be described by radiation resistance. It is 20 times pi squared times C divided by lambda, all to the power 4 times n squared. Okay, so this is our construct. And by the way, if this is, actually we can also have a look. We said that we had some values. So we said that whenever A it is smaller than 5%, sorry, 5%, we had the case when A it was larger than 5% to 50%. Okay. And there was also a case when A, it was larger than lambda over 2. So these were 4 different regimes that can be considered for the antennas. Okay. When you say 5%, often in the book, it's something like this, lambda divided by 20. Here, this is lambda divided by 2. Here we have A, this is lambda divided by something else. Now, let's come here. So we have C divided by lambda to the power 4 times n squared. Now, in this place, we just need to substitute. So this whole thing, we should, so the question is, what should be n in order that this resistance of the antenna would be equal to the impedance of the transmission line. Okay, so this is what we are going to assume. So in this case, C divided by lambda, from here, we get C divided by lambda, this is equal to 1 over 3. So if this is 1 over 3, we get 20 pi squared times 3 to the power 4, yes, times n squared, this is equal to 250. Then we can simplify somewhat. This is 0, 0, this is 25, and this means that n should be equal to the square root of 25 times 3 to the power 4. This is also square root divided by square root of pi squared. Actually, I know that I should not, I can write right away pi. What is left? 1 over 2. So here we have times 1 over 2. So then n, this is 5 times 3 to the power 4 to the power 1 over 2. This is 3 squared times 9 divided by 3.14 times 2. So this is something like approximately, we can cancel this 2, this is 315 divided by 2, this is around 7.5. So it looks like we can have, for n, if we use loop antennas, if we use, let's say, it could be either one, we can find visualized closest. If we use 7 loop antennas or 8, it's still okay. So we can expect a good match between the impedance of the transmission line with the impedance of the antenna. Now, other than this, we can, okay, so we found the 8. Now, if we found the 8, this would mean, but this is approximate, okay, so when you say, so let's use 8 then for a moment. If we substitute, wait a second. Yes, it's 8, right? 5 times 3, 5 million. We simply do, okay. Let's pick 8. You can also pick 7, right? Let's pick 8. And if we pick 8, we know that this is not going to be equal to this number. Okay? So we are going to have some reflection right at this point. So since they are not equal, this was a discrete value. So then this means that we have the RR, it is realistically equal to 20 times pi squared times c divided by lambda. It's equal to 1 over 3 to the power 4. So this is 3 to the power 4 times n squared times 8 squared. So if this is times 8 squared, we should find an expression for the resistance. Let's try this here. So we get 20 times 3.14 times, who can do this faster than me, times 3.14 again, times 64 divided by 3, by another 3, by a third 3, and the fourth 3, we get 155.8. So this is going to be the resistance, 155.8. But why is this the case? This is too much off what we were expecting. Wait a second, so what if it was, am I correct? Can you check the numbers? So this is 20 pi squared, this should be okay. 8 times 8.
Professor, nu ka është model veprimi.
Si?
Ka është model dhe ma veprimi, rezultati.
Ka është dhe, okej, po prisja të ishe pak më afër me këtë. Sepse nën ne shprehim këtu, okay. Nëse përdorim 7 dhe kjo 7 do të rri goxha më larg. Po të vendosim 9, kam përshtypjen jo kaq gjë. Po të vendosim 9, besoj do jetë shumë më larg, një sekond. 158-ën, 155.8, po e pjestojmë për 64, pjestojmë për 64, po e shumëzojmë për...
Del 197.9, diçka e tillë, edhe del shumë afër.
Po kjo që më mirë, po shumë mirë. Atëherë kjo është 197. Se kam prisja që t'i dhe pak më shumë. Shumë mirë, kjo që kam më mirë. Majmë 197.2. 197.2. Dhe po marëm 10 për shumë. Okay, e kam parasysh shumë tjetë problemi këtu. Now I know what the problem could be. Edhe do të them në sekond. We should always, because it doesn't really make much sense. Okay? For a moment, atëherë, sa dole 197.2 pjesëtim për 81 që shumëzon 100. 243, kjo që ka goxha më mirë, fakt. R-ja është barabartë në 243. So we really calculated this value, okay? But this is too much, it is 2 loops off. So if we are to calculate it, you can do even such kind of mistakes. But now the point is that why do we get such a big error? I mean, we can even try 11. We can always calculate this. So let's divide by 100. Let's multiply by 11 times 11. 294. This is equal to 294. Okay. So imagine we are off by almost 100 ohm or 95 ohm. From 156 to 250. Okay, so we have to figure out an explanation. Why did this happen? Okay, let's think for a moment. One reason that this could be possible is that lambda divided by 3. It is not really a small, it's not really a small loop, okay, lambda divided by 3. Let's see how much big error we could have, and by the way, actually once we find these, we can also calculate the reflection coefficients. So for all, so we have all of these are here, so we can find the reflection coefficient here. This is equal to the resistance. Actually, it's an absolute value, so it doesn't matter which one we subtract. We should find the difference between the two impedances, divided by the sum. So here, the difference is going to be 250 minus 155.8 divided by the summation between these two. So this is going to be 250 plus 155.8. And we have to find what this is equal to. So then, this reflection coefficient is going to be equal, so we don't need to write. Can someone calculate this? But it looks like this will be equal, the reflection coefficient, 253, this is 7, this will be 7, divided by 483. So here we have the smallest reflection at the point where the transmission line makes contact with the antenna. So here this is 250 minus 197 divided by 250 plus 197. So this is 7 divided by 400, so this is around 7 divided by 500, or approximately 10 divided by 500. This goes out. So let's multiply by 2, this by 2, so this is like 2%. It looks like we have approximately 2% loss because of the reflection coefficient, okay? And here, we can, this is 294, the difference with respect to this one, this is around 44. So this is 44 divided by almost 300 plus 250, it's 550. So you can calculate the errors, but this looks something like 8 to 10%, 8 to 9% reflection coefficient. Now, let's try to determine why do we have such a relatively different mismatch between the precise value of n, while here we got something like 7.5. One thing that could be is that this loop, it's not really a small loop. These approximations, they are often used for small loops, which will be, imagine for a moment that this is lambda divided by 6, okay? If we do this lambda divided by 6, the numbers that we will have to deal with will be so here we have RR will be equal to 20 pi squared. This is C divided by lambda. C divided by lambda, this will be 1 over 6. So this is 6 to the power 4. 6 to the power 4 times n squared. This is equal to 250. Now we have to find n, and for this one, we can take, so these are equal to each other. We can divide by 10. Now we can apply the square root, but wait a second. Oh, we have a huge mistake here. We have to take the square root of 2. Okay. You see? Now I see it. So apparently our mistake was right here. Okay. I missed this one. So we cancel out the tens. We took the square root of, because square root of n squared is n, square root of 25 is fine, that's easy. But this is the square root of 2. If this would be the square root of 2, then 3.14. Let's try to get a more precise value. So that's why there was a mismatch. It shouldn't be this large. I was trying to argue after this mismatch between, which is like from 7.5 to 10, I was trying to argue that maybe we should have a smaller loop where the error would be smaller. But now let's see what we get. So this is, okay, square root of 2 is 1.4. So this is 5. You can also do the calculation faster than me. Square root of 3, 4 times 9 divided by 3.14 divided by 1.4. We get 10.24. Okay. Okay, so this was our mistake. After we correct this, this will be rather 10.24. Okay, then now I feel better. So, yeah. So this is the case. But now, and by the way, let's have a look. The difference between this 10 and this 10.24 is very small. But since we started doing these calculations, let's get this done also for a smaller loop. So this is a circumference which is half of the previous one, and let's now see what is n. N should be equal to the square root of 25. It's 5 times 6 times 6 divided by pi divided by the square root of 2. Okay. So then it looks like we need a much larger number of loops. 5 times 36 divided by 3.14 divided by 1.4. We get 40.95. So simply n is approximately 41. Okay. Yeah, so there is not much essential difference actually. So now, just because of a small mistake, we just went a little off. But then let's see, our r is going to be equal to 20 pi squared times times 1 over 6 to the power 4, 6 to the power 4, because this is 6 to the power 4, times n squared. So we get 41 squared times 41 squared. Yeah, I think there's no need to calculate this again. We should be fine. This is 3.14 times 3.14 times 20 times 41 times 41 divided by 25577. Anyway, so 25577. 25577. There is no need actually to assume that probably it could be. So here we get a difference of around 7 ohm, and here we get a difference of around 5.7 ohm. From here. Anyway, so we can also try lambda divided by 10 and see how much you get closer. But okay, so this is an important relation. But we all do this relation in order to figure out how much losses do we have because of the reflection. Okay. Now we can stop here for today. Do you have any direct question? Any question that you might
Pyetje jo, po në qoftë se është e mundur të na